Find the biochemical oxygen demand after 5 days at 30 degrees Celsius in milligrams per liter. In this problem, 10 milliliters of a sample is diluted with 490 milliliters of water at 20 degrees Celsius. Initially, the solution is saturated with dissolved oxygen, and after 5 days, the dissolved oxygen measures 5.7 milligrams per liter. There is no chloride in the sample, and the temperature variation constant and the deoxygenation rate constant for 20 degrees Celsius are provided. The biochemical oxygen demand at a time t in milligrams per liter equals the ultimate biochemical oxygen demand, BOD sub U, in milligrams per liter times the quantity 1 minus 10 raised to the minus 1 times the deoxygenation rate constant, K sub D, in units of 1 over days, times the time, T, in days. From the problem statement, we know to use a time of 5 days, but we don't yet know the ultimate BOD or the deoxygenation rate constant for 30 degrees Celsius. We'll begin by solving for the ultimate BOD. The ultimate BOD equals the BOD at a given time period divided by the percent change between initial and ultimate BOD up to that time as a decimal. From the plot of BOD versus time, we notice the ultimate BOD is temperature independent, which means the ultimate BOD at 20 degrees Celsius equals the ultimate BOD at 30 degrees Celsius. And we can solve for the right-hand side of the equation for any temperature. Using 20 degrees Celsius, we know the deoxygenation rate constant, K sub D, but we don't yet know the time, T, or the BOD at time T. Since we've been given data for the concentration of dissolved oxygen at 5 days, we'll use a time T of 5 days, and then solve for the BOD at time of 5 days. The biochemical oxygen demand of a sample equals the change in dissolved oxygen concentration of that sample times the dilution factor, dF. The dilution factor equals the total volume divided by the aliquot volume of the tested sample. Plugging in the given volumes for the sample and water, the dilution factor equals 50. The problem states the concentration of dissolved oxygen at 5 days equals 5.7 milligrams per liter, and the initial sample is saturated. The concentration of dissolved oxygen in a saturated sample, free of chloride and at 20 degrees Celsius, can be looked up in a table, and equals 9.17 milligrams per liter. Next, the dissolved oxygen concentrations and dilution factor are plugged into the equation, and the 5-day BOD at 20 degrees equals 173.5 milligrams per liter. At this point, we can return to our equation for the ultimate BOD. Plug in our values for the 5-day BOD and deoxygenation rate constant and the time, and the ultimate BOD equals 241.6 milligrams per liter. Returning to our initial equation for the biochemical oxygen demand, we have the ultimate BOD and the time, T, at 5 days. But we need to determine the deoxygenation rate, K sub D, for a temperature of 30 degrees. From the plot of BOD versus time, we notice that the reaction at 30 degrees Celsius is faster than the reaction at 20 degrees Celsius. So after a certain time period, there will be a higher biochemical oxygen demand in the sample with a higher temperature. The deoxygenation rate constant can be converted between two temperatures by knowing the deoxygenation rate constant at one temperature and the temperature variation constant, theta sub d. The deoxygenation rate at 30 degrees Celsius equals 0.174, day to the minus 1. Returning to the original equation, the solved variables are plugged in, and the 5-day BOD at 30 degrees Celsius equals 209 milligrams per liter. Looking over the possible solutions, the answer is C.